In this video, we present a demonstration of real-time ray-traced global illumination on NVIDIA RTX in Metro Exodus. Ray tracing has long been regarded as the standard for offline rendering due to its ability to accurately model the physical behavior of light in the real world. A single ray trace operation searches for the shortest, straight-line path between the pixel currently being drawn and some arbitrary polygon elsewhere in the scene. This search can end up potentially landing on any given polygon anywhere in the entire scene, and with polygon counts ordering in the millions, this can be a very long search indeed. This is why ray tracing has earned itself a reputation for computational intensity. The Turing hardware in NVIDIA RTX is capable of performing many of these searches simultaneously. In the scenes we present, several 100 million such rays are cast every single second. Even at these rates though, we still need to be strategic about how we use each ray, since this equates to a budget of roughly 3 rays per pixel per frame. And so we made decisions right from the start about how best to utilize these rays to get the best results for Metro Exodus. The scenes currently playing give us a much deeper look into the demos that we presented at Gamescom, directly comparing our old and new lighting technology. They are captured in-engine during the course of actual gameplay on an RTX 2080 Ti at a resolution of 1080. Performance differences between RTX on and RTX off attest to the cost of ray tracing algorithms, but also demonstrate the high performance of new cards using conventional rendering techniques. We see how light streaming in through the windows and open doorway bounce off of the brightly lit floor and transfer some of the information to the ceiling, the walls, and objects which would otherwise be in shadow. These parts of the scene do not have a direct line of sight of the sun, and so would otherwise be completely black if we only used a single directional light source, and we were to not perform other checks for secondary lighting interactions. Global illumination aims to model how soft, diffuse light bounces around the scene to reach the dark, shadowy recesses hidden from view of regular direct light sources. Conventional global illumination systems are actually a product of a number of subsystems working together to create a final image. To approximate ambient light, we would have spent a lot of time placing and tweaking subtle point lights. These help to add soft light to the occluded regions but are not representative of true physical lights, and so appear noticeably unnatural. With RTGI, rays generated by surfaces in these dark regions sample other surfaces in the room to calculate how much light is reflected in their direction. This allows any arbitrary surface in the scene to act as a subtle area light source, and it allows us to calculate at a much more accurate, per pixel level, how much light should be received from the environment. Our algorithm works by having each pixel dispatch its set of rays in a pseudo-random distribution in a dome above the surface that that pixel belongs to. By applying a filtering process, which makes use of the rays created by the surrounding pixels and by rays generated in the previous few frames, each pixel will ultimately have access to the information of many cast rays in many different directions, and thus have access to many tested surfaces to determine how much light should be reflected from the environment on towards the camera. By removing the additional lighting methods, we not only reduce the amount of time that we would have spent fine-tuning these scenes, but also those dark hidden surfaces now accumulate light automatically. Also, they can respond dynamically to new lighting situations, rather than being stuck with a pre-built solution. Light in the real world travels effectively indefinitely until it either reaches the surface we are rendering, or is blocked by another surface. On the inside and underside of this vehicle, we see how screen space ambient occlusion alone would not be enough to generate realistic shading. Screen space ambient occlusion limits us to the information contained in just a small region of pixels surrounding the rendered point. The area that these pixels cover may have been as small as just a few centimeters across in the real world. A few centimeters with which to say which directions light is ultimately blocked from and which it is not. By casting rays over long distances, we can safely determine how many or how few rays reach the target pixel. Regions of the scene that are large and open enough to not be shaded by screen space techniques, but which still have very few direct lines of sight of the bright parts of the scene, now darken appropriately. Without casting rays over a significant distance, sometimes many meters, we cannot, for example, determine how little light should penetrate the enclosed architectural features, vehicles, or deep into the mass clutter of objects. Since light can reach the point being drawn from any direction within the dome above it, casting rays in random directions above the surface allows the surface to respond to many large, irregular light sources, independent of where they are in the scene or how they move relative to that point. The results presented here demonstrate a technique that simplifies and improves upon the previous generation of techniques by combining disparate rendering technologies into a single unified algorithm. This new ray-traced global illumination algorithm benefits from access to a wider range of scene information and greater physical accuracy, and enables the creation of more realistic and more believable environments in potentially shorter development times. RTX assists in creating open, natural environments as well, lit appropriately according to the contributions from sunlight alone. This concludes our presentation. Ray-traced global illumination will be available in Metro Exodus on NVIDIA RTX technology on February 22, 2019.